Hey students, I wanted to take a moment and introduce myself. I'm Dr. Tracy, or Dr. T as I kind of brand myself, I guess you might say here. You're about to embark on a semester of physics, well, a couple semesters for many of you, and to reintroduce you to a topic that you've encountered previously in your studies, or at least according to the registrar you have, a topic that will also be extremely useful to you throughout the entirety of the first semester and significant parts of the second semester. And that topic is trigonometry. Now, a lot of students come to physics and it's been a minute since they've taken trig, and so reintroduction to the topic can be a little bit rocky. So what's going to follow in this video is I'm going to walk you through the basics and then give you a bit of a behind the scenes look at sines and cosines and tangents to some extent, and then wrap it up with some peripheral references on how you will be using this in your studies. So physics is a very intimidating topic to a lot of people. Our job is to try and make it not intimidating. The material that you learn here will serve you in your career, so hopefully by reintroducing yourself to these topics of sines, cosines, tangents, understanding why we talk about them the way that we do and why we use them the way that we do will help you be more successful and more comfortable with physics and its role in your studies. So let's get to it. So welcome to my board. And this is one segment of a lot of boards. You've seen whiteboards before, but I want you to just kind of know that you're going to always see this box up here. This is the steps of how to solve problems in physics. So if you ever get like stuck, or like, I don't know, someone bonks you on the head by accident and you're like, wait a second, how do I solve problems? That's your tip right there. So take a look. I got a lot of stuff written up here. We're going to go one step at a time, so don't let it intimidate you. And you're going to come into the lab. Sometimes I'm going to have stuff written on these boards for different reasons. Please don't let that bother. If you feel intimidated, let me know. Go knock on my door right across the hallway and say, Dr. T, it's too much. And I'll be like, you're right, and then I'll get rid of it, okay? But by and large, the stuff that's up here is going to be useful for you. So just kind of take it one step at a time. Don't rush. So let's dig in. What is trig? Well, what's a crazy word, trigonometry. But it's all about the triangles, right? You remember the triangles? We got the triangles that have, the different types of triangles. You got the scalene and obtuse and acute triangle, and then there's the right triangle. We call this the right triangle, if you may recall, because one of the angles inside the triangle is a right angle, 90 degrees. That's good. All right. No harm there. You may recall that we have three sides to the triangle, which we label A, B, and C, just because, right? And we've indicated in this triangle that there's an angle that's of interest. Why is it of interest? That'll come. Don't worry about that just yet. We'll get to that. And this longest leg, which we refer to for right triangles, is true. It's the longest leg. We call that the hypotenuse. I'm not really sure why. Let's look it up real quick. Hypotenuse. Wikipedia is the bomb. All right. Oh, etymology. Says here, subtending the right angle. I don't know what subtending means. I do. I just, trying to relate, So there you go. Greek word that means has to do the opposite of the right angle. So hypotenuse, this is the standard drawing for right triangle. You can have them different directions and what have you. Just remember to always identify that right angle by its 90-degree appearance, and then your angle of interest. You'll notice I've drawn a theta, which you probably recall, and then another one that we call phi or phi. Most people call it phi. But if you're a stickler for proper early Latin enunciation, then it's phi. So, Greek letters that you're going to see a lot in this semester is theta, phi, or phi, alpha, beta, gamma, delta. This is all going to show up. There's a couple other ones, rho. Is another one, but for as far as like angles are concerned, when we're talking about trig, theta, phi. Occasionally you'll see these, but that's only like generalizations, derivations, and stuff like that. That'll come. So, what do we do with these? Well, I do recall way back when, move the cobwebs out of the way, SOHCAHTOA. Aha, SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, that's a memorable word on its own, right? SOHCAHTOA. Tangent is opposite over adjacent, which, if you look at the math on here, that's just the sine divided by the cosine. So you end up with, for sine opposite over hypotenuse, it's B divided by C. And then adjacent over hypotenuse, that's A divided by C. That's adjacent, that's the one that's touching the angle. And then tangent, B over A, the opposite over adjacent. So just some refresher on some of the stuff. This is the main bread and butter for the first several weeks. You also recall our good friend Pythagoras, who said there's an interesting relationship between the lengths of the sides and the hypotenuse. That's a squared plus b squared is equal to c squared. And we're going to use mostly of these two right here, the tangent and this one, to go back and forth between certain concepts. So that's going to come. I just want to kind of ease you guys back into these concepts. But now, this is the basics. Stay tuned. In the next segment, I'm going to talk about kind of where sine and cosine come from, because they really came out of nowhere for you, I think. Whenever trigonometry is introduced, we just say sine and cosine have these relationships, and tangent follows suit. And you may have heard other insanities such as cotangent, secant, cosecant, hyperbolic tangent, hyperbolic cosine, hyperbolic sine. If you've played in those sandboxes, good on you. But this is the wheelhouse right here. This is where we stay. This covers everything for this term. Stay tuned. So to do the SOHCAHTOA stuff and the calculations, you need a calculator. You also need a protractor, which I'll show you in just a second. 3, 2, 1, now. So protractor is a ruler for circles. What else can I tell you? No, tease you. Okay, so as you recall that there's usually an inch scale and a centimeter scale ruler on these. There's a little dot right here and right here that will help you with alignment of something that you're trying to measure the angle compared to. And as you can see, most scales, they have both directions going on them. So 0 to 90 to 180 and 180 down to 0 again through 90, and allows you to make the measurements. These are measured in degrees. I don't know that I've ever seen a protractor measured in radians, but who knows? Maybe somebody will invent that. Maybe one of you guys will invent that. So let's take a quick look. So let's say somebody measures this vector. So you take your protractor, set your center point right at that interaction. You see this is aligned poorly, so we'll do that. And you would measure this to be, sorry, you gotta look at the inside track. So this measures 10, 20, 30, 40, about 39 degrees. And if this is east and this north, you would write that 39 degrees north of east. This is the angle here. And if we want to see that triangle, we're not going to do it right now. Got to save something for the professor to do. And as you just saw, the ruler, so that you can measure the lengths of the legs and so forth. But what you see behind me is how do we get to these ideas of sines and cosines? Where can we think of them as coming from? And the answer is polynomials. Keep it simple. You've seen something like this before. You notice I've got some pre-designed ideas for what functions should go on each of these little graphs that I've put over here. So let's do each one as you may recall. Y to the x. That should have been y equals x, not y to the x. So I'll do that again. Y to the x. So let's do that one again. Y equals x, drawn. And it's just a straight line. It comes from lower left, it goes to upper right. Okay, seen that before. No surprises. That's good. All right, what about y equals x squared? You may recall that that's called a parabola. It's also referred to as a parabolic function or a second order function, quadratic function, quadratic equation. All those things are all jumbled together and associated with parabolas. It will show up again in lecture. It will show up again in lecture. So just kind of be ready for that. But the graph, you recall, looks like a U, goes on forever in both directions. And the key thing I want to highlight for you is that on both of these two, there's something they kind of have a pattern already start to notice. The right hand side goes up to the right and on both cases. And for the negative, in this case it's kind of switched. This one's gone down, this one goes back up. So if you are just thinking about that pattern, maybe you're spotting the potential for the next trend, and you can do a Google search on a third order function, third order graph, and at y equals x cubed, or you may just recall where now it has, again, it's going up to the right in every case, but on the left hand side it's turned back down. It doesn't go straight, it does a little curvy thing, and then it goes back down. So you can kind of see the pattern going here. Y equals x to the fourth. Now if you do y equals x to the fourth and these higher order functions exactly like this, the graphing calculator is just going to be like, it's not going to be as detailed as what I'm doing. You need those second and third terms, y equals x cubed plus 2x squared minus x to the first, and so on. So, but the main point is that looking at the pattern of these things going, so y equals x to the fourth flip-flops again, and both sides go positive, and y x equals fifth, as you might guess. Y equals x to the fifth, again, they flip-flop back and forth. And you start to notice something that's happening here. You've got this confined region between your extremes where the graph doesn't go very far from the center axis, but the outer ends, they go far away. So what happens if we had a term that had an infinite number of components, x to the 16th, and x to the 22nd, and stuff like that? Well, you basically have this wiggle that goes on and on and on until you get to those ends, and off you go into the stratosphere. So we write a polynomial, a very special one. There's not at all intuitive. This is not something that you would sit there having a snack over at the muck and you go, I'll bet if I wrote this equation exactly this way, probably get something interesting out of there. I mean, you might be, super genius in this sense, but it's not intuitive. It doesn't jump out at you and you go, oh, this is obvious. If I had a graph that went all the way to infinity and all the way to positive infinity and stayed within this range between positive 1 and negative 1, the polynomial would look like this: x to the first power minus x to the third power divided by 3 factorial. And I don't know if you've ever run into factorials before, but that's just 3 times 2 times 1, 5 times 4 times 3 times 2 times 1, and so on. Plus, the signs alternate. And these are increasing by 2, but they're all odd numbered exponents to the 9th, to the 11th, and so on. We give this a function a name. It's a very special function, a very specific function. It does a very specific thing. It stays within a very particular region, positive and negative. It doesn't go too high, doesn't go too low. And it continues on repetitively forever. We call this a sine function or a sinusoidal function. And those of you who are in the medical field should probably already be familiar with repetitive periodic functions in the form of a sinus rhythm. So I've got it written here, as we've been doing, everything's with x, but we don't really deal with x with sines and cosines, at least not in this class, when we're dealing with things that are actually angles and locations relative to other locations. So I'm rewriting it for you to see it. Sine of theta, theta to the first, to the third, and so on, written in this way. This is what a sine is. It can be represented by a bunch of polynomial terms that are jammed together into the same graph, and it has very special qualities. Repeats itself, goes on forever, stays within a narrow band up and down. So you say, okay, well, sine, sure. What about cosine? Glad you asked. Similarly, if we have one, notice this one starts right at 0. So when x is 0, all the terms are 0, the function is 0, it's right there at the origin, and sine of 0, 0 angle is 0. But there are points where it's exactly opposite from 0. It's at positive 1 or it's at negative 1. What does that function look like? Great question. Well, it turns out that if you take all the even number, and remember x to the 0, 0 is not really an even or an odd number, but it is in the pattern of an even number. So x to the 0, x to the squared, x to the 4th, x to the 6th, all over those related factorials. Again, alternating sign. And again, this is just built off of taking all the even numbers of these, sticking them together, and on to x to the 30th, x to the 924th. Becomes cosine of x, or in terms of theta, cosine of theta, and on. You don't need to know any of this. But I believe that when you do know where kind of things come from, it's not just a thing that physicists use because we want to make your life miserable. We don't. It's just we like what we like our sandbox, right? But when you understand where these things come from, it gives you a better sense of usefulness. It's not just something that we say, well, let's just come up with this weird word and call it a sine and a cosine, and then go even further and come up with something called a tangent. There's a mathematical explanation for where these come from. Hopefully this is giving you a little bit more of a clarification on that, and you can feel a little bit more comfortable with the idea that sines and cosines are more than just tools in the toolbox. They actually have mathematical meaning. So let's take a look at part 3. What's the point? I made you watch this video, and maybe you're wondering what is the point of watching this video? Okay, maybe you knew this, maybe you didn't know this, but I did want to kind of just give you like a little sneak peek as to where this all ends up. Where does it take you? And the answer is that throughout most of the semester, you're going to learn a lot of stuff. You're going to learn a lot about mathematics and its use in physics as a tool of science. You will find out a lot about how to measure all kinds of stuff that you may or may not have ever thought that could or should be measured. And one of the simplest things is this idea of vectors and vectors and scalars. Now, again, you'll cover vectors and scalars in class, but the general idea with a vector is it's a measurement where direction matters. When you think about it, we use vectors every day in life. If I told you to walk for 1.6 miles east from here, and you were looking to go to, say, Hy-Vee or Walmart, well, I just gave you the wrong directions, because even though 1.6 miles is the correct distance, it's not the correct direction. So one thing that you'll learn to do is you'll say, okay, I've got this arrow, this line, this vector, this ray, whatever, that has a distance that you measure the length. You can put it against a grid, an XY grid, in a way that's convenient, that makes the most sense and makes it easiest to solve the problem. And you'll get the knack of this as time goes on. But you draw an XY axis relative to some set of interests, a flat surface of some sort, or north, south, east, west, what have you. And you set this here, like so, aligning everything to make sure that everything is where you want it to be, and then you measure the angle. In this case, it says about 28 degrees. That gets your angle. There's a lot of uses for that. Once you've gotten the skill of doing that, you could face problems where you're predicting where a basketball player would be shooting a ball into the hoop, at what distance, how much time it would take to get there, how high the hoop may be based off of factors that you know, such as acceleration due to gravity. Many of you in the medical field, whether it's going to be a nurse, a doctor, or what have you, or a kinesiologist, you're going to be able to figure out how much force is happening at the bone of the forearm based off of the bicep muscle, even though the distance is very small. You'll learn how to calculate how much friction is applied when you are pulling an object across a surface that has friction. You'll find out the relative angles for two balls that come into collision with each other. There are loads of configurations and situations that you can apply trig to, sines and cosines and tangents, and be able to extract a great deal of understanding and knowledge about those configurations. And it has everything to do with this idea from triangles, sines, cosines, tangents, of an angle, which we call theta. You do need to be aware that there are two ways of identifying angles. I'm just going to tell you theta, the angle, usually measured either in degrees, that's the one you're familiar with, or radians, which we'll cover that. But it may be worth a quick look at Wikipedia or just a Google search to figure out what radians are and their relationship to angles and degrees. So, like I said, the purpose of this video is to give you a refresher of what sines and cosines and tangents are, SOHCAHTOA, the practical use of it in a very superficial way, to kind of let you see where sines and cosines come from in different aspects from mathematics, and to kind of see how it's going to show up throughout the course of the term. Every lab activity that we do in this semester will have a walkthrough video, and in that walkthrough video there is a theory section. A lot of students neglect that section. Please, please, please watch those theory videos. Even if you've got the basic idea or you like to just kind of come in and roll the dice and just go with it, you really are giving yourself an advantage to watch the theory as it's presented specifically for this lab, as well as being a dynamically alternate way of seeing the material compared to how you were exposed to the material in the lecture. We all have different teaching styles, and physics is already exotic enough. Let's work together to give you the best opportunity for success. We're making sure that you take a look at the theory, not just in the lab manuals, but also in the walkthrough videos. Back to me. So there you have it. Trig, a refresher, a little bit of a dip into vectors and why we call these things sines and cosines. And hopefully you feel a little bit more refreshed on the concept, and come back to this video and rewatch it every once in a while when you're actually going through the material in lecture and when we do it in lab. It's definitely there to make your life easier to the extent that we can do. And if you have any questions, of course, you've got me, your TAs, you've got your instructor. Don't forget that there's Physics Help Center, and ask for help when it comes up. All right, that's what we're here for. Hopefully you find new insight into trig and sines and cosines, and thanks for watching. You guys have a good start to your semester. We'll see you in the lab. Now I wanted to take a few minutes to write to write. What is the actual reason? Hey Google, what is it called hypotenuse? I thought that was funny. My daughter said it wasn't, but she was laughing at the same time, so mixed signals, right? And then you set that there, and hypotenuse, meaning subtending the right angle. There you go. I can read your thoughts. You want to bring Dr. Tracy some tacos. Just kidding. Ooh, it's 3 Musketeers.
I got to clean on my hair.
It's so messed up that they don't make a 4th Musketeer. The D'Artagnan bar.
Yeah.
You can check my work. Whiteboards. And I'll give you your angle.